This is section 3.1, Extrema on an interval. All right, so now we're going to be, in this chapter, talking about applications of differentiation. Beyond knowing the slope of the tangent line and giving you a rate of change, there are other things that you can do with the first derivative. So in calculus, there's a lot of effort that goes into looking at a function f on a given interval I. What's it doing? Is it increasing? Is it decreasing? Is it concave upward? Is it concave downward? Is there a maximum? Is there a minimum? All kinds of things that we'll talk about in this section, in this unit. So one of those is, does f have a maximum value on the interval I? Does it have a minimum value there in that interval? Where is it increasing? Where is it decreasing? These are some of the first questions we will address. Then we'll apply that to real life problems and give you a sense of why we're doing all of this. So let's start with the definition of extrema. First of all, we're going to have a lot of words that are in their singular or plural form. So I'm going to give you some of these. This is the singular, one extremum, and the plural of that is extrema. It's one of the first words we're learning. A maximum, if you have one of them. If you have multiple ones of that, that's called maxima. And minimum, can you guess what its plural form is? Yep, that's minima. And by the way, you probably know what a maximum is and what a minimum is. An extremum is a one-word way of saying it could be at the high or low end. It's at the extremes of the values of the function, so extremely high or extremely low. So an extremum, it can be either a maximum or a minimum, and it's a one-word way to capture both ideas in one. Okay, so let f be defined on an interval I containing the number c. Number one, f of c is the minimum of f on the interval I when f of c is less than or equal to f of x for all x in I. Okay, so let's say we have a function, and here's our interval, and I guess I can define that. It goes from a to b. And let's just say that this is the y-axis over here, this is the x-axis, and this is our function f on the interval I. And what we're saying is that f of c is called a minimum when f of c is less than or equal to any f of x you pick on the interval I. So on the interval from a to b, f of c is less than or equal to all function outputs from a to b. Okay? So when you see the picture and put this together, it makes a lot of sense. So number two, f of c is the maximum of f on I when f of c is greater than or equal to f of x for all x in the interval I. So see if you could draw a picture that represents that. You've got the picture on the left to help. Okay, so I'm starting to draw my picture. And you have a maximum at c when f of c is greater than or equal to all the function outputs on the interval from A to B, which is what I'm calling I. Okay? So that's what it means to be a minimum. And what it means for C to be, or f of C to be a maximum. And there, I almost misspoke, and so let me make sure you're clear about what is the maximum and what's the minimum. The maximum is the y value f of C. When I say find the maximum, whatever y is measuring in, let's say that's the population. What's the maximum population? I'm looking for a value of y, in that case population. So it would be f of C that is the maximum. It occurs, the maximum occurs at C, the x value. But the maximum value itself, the maximum is the y value f of C. And the same thing is true over here with minimum. If I ask you for the minimum, I'm looking for the y value. If I ask you where does it occur, or what's the x value that creates the minimum or maximum, then the answer would be the x value of, in this case, C. So be careful that you understand those words and what they're looking for. So I'm going to read some of the vocabulary in the definition of extrema and try to highlight some things to make sure that you've got these clear. The minimum and maximum of a function on an interval are the extreme values, or extrema, and they give you the singular form like I did, of the function on the interval. The minimum and maximum of a function on an interval are also called the absolute minimum and absolute maximum, or the global minimum and the global maximum. So these values that I called minimum and maximum are also called absolute min and max and global min and max. And they all mean the same thing. Well, minimum means minimum, maximum means maximum, but other than that, you can put those words absolute and global in front and it means the same thing. Extrema can occur at interior points or endpoints of an interval. Extrema that occur at the endpoints are called endpoint extrema. So I didn't have one, well actually I do. If you look at the first graph, the maximum value on I for the maximum occurs at B, and f of B is the maximum. And it happens to be an endpoint maximum. And over to the left, f of A is the minimum. And it also happens to be an endpoint minimum just because of the way I drew the functions. Okay? So, now, a function doesn't have to have a minimum or a maximum on an interval. And there are a couple of ways that could happen. One, if I had a picture similar to the one I just drew, except this were an open circle, then this graph has no maximum because the only candidate for it is at an open circle, and there is no value that it actually reaches that's a maximum. You can say it's bounded on the top by that value, but it never reaches it. And so let's just say that's 4, for example, where the open circle is. 3.9 is not the maximum because there's a number bigger than that, 3.99. 3.99 is not the absolute maximum because there's a number bigger than that, 3.999. And so you could do that forever. And so there is no maximum on this graph. It's also possible that if I had a graph that looked like this one, had an open circle here, that one would have no minimum. So what is it we could do to guarantee that we'd have a max and a minimum no matter what? Well, the things that are happening that are saying you don't have to have a maximum or you don't have to have a minimum is the fact that the first one, going from A to B, that interval includes A but does not include B. And so if the endpoint isn't included, and that's the only viable candidate for, let's say, a maximum or a minimum at B, and there's not one, then we don't have to have one. And in this case, let's say this is A, and this occurs at C, and this is B. The interval here goes from A to C, union C to B. In other words, there's a discontinuity at C, and that means we don't have to have a max or min. So to guarantee that you'll have a global max and a global min, and I will abbreviate these like this, so you may too. If you're writing something about minima and maxima, it's fine if you use the abbreviation. You will have a global max and min guaranteed if your interval is a closed interval. In other words, you've got to include both endpoints, not an open interval like that one on the left is open at B. You have to have a closed interval, and you have to have continuity. On that interval. So again, there's the continuity idea again rearing its head. And you know, when we talked about continuity, you may have been thinking, oh my gosh, what do I need this for? Well, you can't say you definitely have a global max or a global min unless the function is continuous. And so again, it's really, really, really important that you have continuity. So that leads us to theorem 3.1, the extreme value theorem. If f is continuous on a closed interval a to b, then f has both a minimum and a maximum on the interval, guaranteed. So this guarantee is the extreme value theorem is your guarantee that both will exist. Okay, so, oh, and by the way, it would not have mattered if, even if at C I had a value defined at C that's not where the hole is, I still wouldn't have a minimum there. So it isn't because f of C is not defined, it's because it's a discontinuity. All right, so let's use the theorem 3.1, the extreme value theorem, and see what we can do with it. F of x is x cubed minus 3x squared. And since that's a polynomial function, we know it's continuous on any interval you want to have. And if we graphed this, let's see if I can get a graph here. It would look something like this. Not a perfect graph. Okay, so if I were to pick any subinterval of that, let's say from, oh, I don't know, 1 to 3. Let's do 1 to 4. 1 to 4. Can we find the absolute? So That's just a synonym for global. Can I find the absolute min and max on that interval? That's going to be a question. And so from the graph, what you'd want to do is find out what the y value is at 1. So let's just say it's about right there. What's the y value? Well, let's see. F of 1 is 1 cubed minus 3 times 1 squared, which is negative 2. Okay, so that's a value of negative 2. Visually speaking, this point down here looks like it's a low point, and we'd have to find out where that happens. And I'll just tell you right now it's at 2, negative 4. We'll later figure out how to find that. But we're just going off of a graph that let's say that we've done a really good job of graphing, and we can find all of these points easily. And then at 4, 4 cubed minus 3 times 4 squared, 64 minus 48 is 16. I believe that's correct. And so at 4, say this point right here is at 4, 16. So looking at those points and looking at the graph, would everybody agree with me if I said the absolute max is 16 and the absolute minimum isn't that negative 4? Yeah. So you can see that this isn't that bad of a question if you're just looking at a graph. Just look for the highest and lowest point. No big deal. Okay, now we're going to turn to another idea, and we're going to use the same graph, and I'm going to probably redraw it because those labels there aren't helping me necessarily. So same function. Okay. Right. So here's the graph. Now this graph, if you look at the entire domain, which by the way is an open interval from negative infinity to infinity, are we guaranteed an absolute min or an absolute max? Well, no, because it's an open interval. We can't say that necessarily. But we can say, by looking at the graph, that it will go down forever and go up forever. So there's absolutely, sorry, it's a bad pun. There is absolutely no absolute minimum value and no absolute maximum value. But I want you to focus in on a small region, not the entire interval, but if you were to look inside of this box only, would you agree that there's one point on that graph inside the box that is at an absolute greatest within the box? Yeah, and what we're going to call that point, because it's only in that vicinity, in that region, where that's a high value for that region, we're going to call that a local maximum. It's not a global maximum, because that involves the whole function. And we weren't given an interval I like from a to b this time, so we're looking at the whole function. It's not a global maximum, but it is in its vicinity the highest value. By the same token, can you find a local minimum? Well, inside of this box, looking at just that part of the box, is there one value that is the lowest of all values in the box? Yeah, that's right here. And we're going to call that a local minimum. And there are so many textbook authors that you get lots of names for things. We have the global maximum. We have the absolute maximum. Those are synonymous. Besides calling this a local maximum, another term that's used by some textbook authors is they'll call it a relative maximum. So relative to all of the other points in its immediate vicinity, it is relatively high compared to all of them. And what do you think we'll call the local minimum, in other words? Yep, it's a relative minimum. So there's all kinds of vocabulary associated with this, and it's confusing because there are a lot of synonyms. Local and relative here mean the same thing. Absolute and global, from what we talked about earlier, mean the same thing. And so I get it. There's a little bit of confusion. Okay. So that's what we'll call a local or relative extremum. Now, if you'll look at those extrema on this particular graph, what's true, because we're going to relate this to the derivative that we did earlier in this course, what's true about the derivative at the local maximum in that particular picture? Wouldn't you say that the derivative at that point is equal to a particular number? Doesn't that have to have a horizontal tangent line at that high point? So isn't its derivative 0? Is that true for our other one? Does it have a horizontal tangent line there as well? Yes. So that's one way to identify where you might have a relative minimum or a relative maximum is if the first derivative is equal to 0. Then you might have a max or min. Before you get too far into thinking that has to be true, let me burst your bubble a bit. Sorry about that, but I hate to say anything and then have you go, oh, but so it's always true. No, not quite. If you had this function, y equals x cubed, let's say is what it is. At 0, 3x squared is its derivative, so 3 times 0 squared is 0. So at 0, there's a horizontal tangent line to this curve. Is that a local max or a local min? No, it is not. It's neither one. And this is called a saddle point, where you have a horizontal tangent line, but it isn't a max or min. And it's called a saddle point because if you kind of think about what a saddle looks like, there's the little horn thing you can hold on in front of you, and then it dips down for your seat and goes up in the back a little bit. Anyway, that's supposed to kind of remind you of a saddle. So if the first derivative is equal to 0, you might have a minimum or a maximum, but it might not be. It might be a saddle point. So at least it's a candidate to be considered as a possible max or min when the derivative is 0, but it might not be that. Now let's switch gears and talk about a different function. And I'll do this one as a particular one on purpose so that you'll know exactly how this would work. I believe we talked about this or something very much like it earlier. I don't know if it's the exact same one or not, so pardon me if it isn't. I meant for it to be the same. Do you remember what the graph of this looks like? I'll give you a second to think about it while I'm getting set up here. Okay. It is something that looks like this, kind of a V. It's 2 rays with a common endpoint, technically. And I want you to tell me what's going on at 0. I mean, where y is 0, at x equals 2. What's going on there? Well, that's a local minimum. And what's the derivative at this local minimum? There is no derivative there. The derivative does not exist at 2. Remember, at corners and vertical tangent lines, the first derivative doesn't exist. So, this is a point where the first derivative doesn't exist. So, this gives us two big ideas about what might give us a local min or local max. Is if the first derivative equals 0, you might have a min or a max, relative min or max. Or if the first derivative doesn't exist, you might have a local min or max. You may say, well, wait a minute, doesn't that always mean that? Well, no, unfortunately not. If I had this graph that has a vertical tangent line, say it looks like this. It actually has a vertical tangent line at this point right here. Whoops, that's supposed to be straight up. Okay, it's a vertical tangent line. That's neither a min nor a max. So no min, no max is possible if the derivative is 0. No min or no max is also possible if the first derivative doesn't exist at a particular place. It's just a way to identify candidates. If the first derivative is equal to 0 or the first derivative doesn't exist for a particular x value, you might have a local minimum or a local maximum, but there's no guarantee that you will for sure. Okay, so let's look at the definition of relative extrema. If there is an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f, or you can say it has a relative maximum at that point. If there's an open interval containing C on which f of C is a minimum, so like inside that box, then f of C is called a relative minimum of f, or you can say that f has a relative minimum at that point. So I didn't draw the box on this one over here. So in that vicinity, close to that point, that's a low point for that curve. It happens to also be, by the way, an absolute minimum there as well. So I'm going to write that down as well, because it happens to be true for that particular graph. It has both a local minimum and, oh, I wrote max. It happens to be both a local minimum and an absolute minimum, not maximum. Wow. It's a local and an absolute minimum there. Sorry about writing the wrong word. Okay, the plural of relative maximum is relative maxima, and the plural of relative minimum is relative minima. I think I already covered that. Relative maximum and relative minimum are sometimes called local maximum and local minimum, respectively. So again, you have all of these synonyms running around, which makes it hard, but some textbooks use one and historically, and some textbooks use the other one, and so now most textbooks include both terms, relative, local, and both terms, absolute, global, to cover all bases, because you never know what someone's going to call it, and so you need to know if they say global and you've always called it absolute, you need to know they're saying the same thing. Or you say local and someone else says relative, you need to know you're talking the same language. Okay, so in example 1, they have some pictures drawn. So I have you look at figure 3.3. Find the value of the derivative at each relative extremum. Okay, so this is kind of what we just got to. So what is, for that relative maximum at 3, for the first figure, what is the first derivative there at 3? Right at 0. And how about for the second figure at 0? What's the first derivative at 0? Correct, it does not exist. And at the relative maximum at pi over 2, what's f prime of pi over 2? What's the slope of the tangent line to that curve at pi over 2? It's 0. And What about at the relative minimum at 3 pi over 2 negative 1? What is the first derivative at 3 pi over 2? In other words, what's the slope of the tangent line at 3 pi over 2 to that curve? It's 0. Okay. So again, those values of first derivative equals 0 or first derivative doesn't exist tells us that there's a potential for there being a local max or a local min at those x values that produce a first derivative answer of 0 or a first derivative that doesn't exist. Alrighty, so let's go to a specific example. F of x equals 9 times x squared minus 3 divided by x cubed. So what we're going to do is find that derivative. By the way, this is the graph of that. The graph of this function is the first one you saw on figure 3.3. I forgot to say that, but that's what this is. So the derivative is low times d high, the derivative of 9x squared minus 27, which I guess I can distribute that on paper to make this easier to do, is 18x minus high, which is the 9x squared minus 27, d low, which is 3x squared, all over the square of low, and if we simplify that, we'll get 81 minus 9x squared over x to the 4th. That's what that simplifies to be. And the question would be, is my statement that f prime of 3, that's 0? I did that using a visual check. I think I'm right, but let's double check that. What's 81 minus 9 times 3 squared over 3 to the 4th? Well, that's 0. Exactly what I guessed it would be. Okay, let's look at the second one. F of x equals the absolute value of x which we really don't like absolute value. It's kind of like we don't like radicals. So we're going to use the definition of absolute value to say that this function is x as long as x is greater than or equal to 0, and the opposite of x as long as x is less than 0. And f prime is going to be the derivative of x is 1 when x is positive. The transition point at 0 is in question, so I'm not going to say or equal to 0 there. And the derivative of negative x is negative 1, and that's true when x is less than 0. And we did something like this earlier. The derivative at 0 is undefined. It's one of those corners. And therefore, it's not going to have a first derivative answer there, because the derivative from the left side would be headed towards negative 1, and from the right it would be headed towards positive 1, and those aren't the same. So at 0, the first derivative doesn't exist, which is exactly what we said right here. F prime of 0 doesn't exist, which is what we said right here. Okay. Then the last one, let's look at the function at sine of x. This is the graph of the third picture in figure 3.3. what is the derivative of sine of x? It's cosine of x. And so let's see if indeed we were correct when we thought that the derivative evaluated at pi over 2 would be 0. That would be cosine of pi over 2, which is indeed 0, as I thought it would be. And at 3 pi over 2, the first derivative at 3 pi over 2 is cosine of 3 pi over 2, which is also 0. So all of my visual inspections gave me the correct derivative answer. So just kind of a little confirmation that I was right. Okay, so let's see. So we can have a local maximum, for example, if there's ever a sharp turn, like this is a local maximum. And if this is at x equals c that happens, and at any corner or sharp turn like that, the first derivative does not exist when x is c at that sharp turn or corner. Or you could have a maximum that looks like this at c, when f prime of x is 0, when x is c. And as I said earlier, that means it's a candidate for a local extremum, not a guarantee. So you do have to look at it further than just finding those places. Now, these places that are candidates for being local extrema are called critical numbers. And critical numbers are numbers that are critical for us to look at to see if we have a local min or max. So the definition of a critical number, let f be defined at c. So there actually has to be something there. It can't be an open circle there, or a vertical asymptote or something. If f prime of c equals 0, or f is not differentiable at c, and I'm going to have a shorter way of writing that. In fact, I've already used it, but this is what the definition says. Then c is a critical number. And as it so happens, if you have a local max or local min, it has to be at a critical number. That's the direction in which the have to points. If you have a local max or min, it has to have a first derivative there that's equal to 0, or one that doesn't exist. So it doesn't go the other way, as I've said a couple of times. If you have a critical number, that doesn't mean you definitely have a max or a min there. It could be a saddle point, or there could be a vertical tangent line, or a couple of examples I showed you already. So that leads us to Theorem 3.2. If f has a relative minimum or a relative maximum at x equals c, then c has to be a critical number of f. That's the direction that it has to be true. So Theorem 3.2 states that the relative extrema of a function can occur only at the critical numbers of the function. Knowing this, you can use the following guidelines to find extrema on a closed interval. Okay, so this is going to find you, by the way, what this is finding you is the absolute extremum or the global extremum. You can use either word. Here are the guidelines. To find the extrema of a continuous function f, that's an absolute or global extrema, on a continuous function f on a closed interval a to b, use these steps. Find the critical numbers of f in the open interval a to b. Evaluate f at each critical number in the open interval from a to b. Evaluate f at each endpoint of the closed interval a to b. The least of these values is the minimum, the greatest is the maximum. That's actually what we did earlier. Let me show you when we did that. This problem right here, the first time we went through, where we found the absolute max was 16 and the absolute min was -4. If we're going from 1 to 4, I found a place at 2 visually where the horizontal tangent line had to be in existence at 2, so that x equals 2 is a critical number. I found x equals 2's y value, -4, then the y value at the endpoint 1 and the y value at the endpoint 4, and compared those. 16, -2, and -4. What's the largest number? 16. So that's the absolute maximum. 16, -2, and -4. What's the lowest number? Well, -4. And so -4 is the absolute minimum. That's, in a nutshell, what we're going to be doing when we follow those guidelines. So it's not mysterious. I don't want you to think it's really hard or anything. This is called the candidate test for finding those, and it's really useful. So if we're asked to find the absolute extrema, find the extrema of f of x equals 3x to the fourth. You notice how they're not saying absolute or global? If they say extrema on a closed interval, that's what they mean, is the global extrema or the absolute extrema. I'm going to keep saying the word absolute or global each time to kind of pinpoint that that's what we're doing, even though they're not saying that. All right, so the first thing to do is to find your critical numbers. The critical numbers depend on the first derivative, so we need to find that. The derivative of 3x to the fourth is 3 times 4x cubed, or 12x cubed, minus 4 times 3x squared, which is 12x squared. And the critical numbers occur when the first derivative is equal to 0, or when f of x is not differentiable at c. So what I'm going to say for that, the short version of that is f prime of x does not exist. I usually start with the D and E thing because that's easy to discover very quickly. Is there any number x that if I put it into my first derivative that would give me a bad answer? And the biggest case of that is if it gives me division by 0. So is there any number x that would have me divide by 0? Well, no, there's no division in this problem. So that never happens. And I'm going to write never underneath here, saying I did consider it. It's never an issue for this particular function. The derivative exists for all real numbers. So the fact that it doesn't exist never happens. That means I can close off that side of it, and I'm done with the f prime of x does not exist side. Now come back over here and solve the equation equal to 0. There's a common factor of 12x squared. Do you see why I said we need to factor? This is why. Factoring makes solving for equal to 0 and doesn't exist way, way, way easier. So this product equals 0 either when 12x squared equals 0, which means x is 0, or when x minus 1 equals 0, that is when x is 1. So those are our critical numbers. Now, we have to pay attention to what we got. This goes from -1 to 2. And so any of the numbers between -1 and 2 that are critical, we include those. Well, both 0 and 1 are between negative 1 and 2, so we're going to actually consider all of them, both critical numbers and the endpoints. But if I had had, for example, an interval I that went from, say, 2 to 8, and I got critical numbers that were negative 3, 4, and 12. Which are the ones that I would consider for finding the extrema on the interval from 2 to 8? Well, the only one that I would pay attention to in that case is the only one that's between 2 and 8, 4. Negative 3 and 12, although they're critical numbers, aren't what we're looking at. So we don't care about those other two, negative 3 and 12. We're only looking from 2 to 8. So it's possible you'll get more critical numbers than you actually will deal with. In this case, both 0 and 1 are between negative 1 and 2, so we have to consider all of them. This is what I always do to make sure I don't miss one and that I don't include one that shouldn't be there. I always start with the beginning of the interval, the lower number, negative 1 in this case. Then I'm going to go through my critical numbers in numerical order. As long as they're bigger than negative 1, they're keepers. So the next one would be 0 as x increases. The one after that is 1. And then I get to my upper bound on that interval, which is 2, and I'm going to use it. So that's the from low to high, the two endpoints, negative 1 and 2, and all of the critical numbers between them, 0 and 1 in this case. So calculate the y value in each case. What's the y value for each one of those? So 3 times negative 1 to the 4th minus 4 times negative 1 cubed is 3 plus 4 is 7. Okay, you go ahead and do all of them. But pause what I've got going, and you find all the rest of them if you would, please. Okay, you should have found the f of 0 is 0, the f of 1 is negative 1, and the f of 2 is 16. So the absolute max is equal to what? What's the largest number you found? Well, it's 16, and that happens to be at the endpoint. So it's an endpoint maximum. And what is the lowest of all those values you found? Right, it's negative 1. So the absolute minimum value is negative 1 on the interval from negative 1 to 2. And that's an interior absolute minimum value in the interval, by the way. Okay. So if you look at the graph of that, and I think I included this graph, but if not, you can graph it on your calculator or look at this. I'm going to try to reproduce it, but it won't be as good as if you put it on your calculator. So you might pause this and graph this function f of x. You might want to set it up so you're only looking at it from negative 1 to 2, because you might get distracted by other things. So only go from negative 1 to 2 on your calculator. And the graph should look something like this. Oops. Well, this graph is going to go right through the number 1. Well, looks something like that. And of course, for your y min and y max, you needed to go at least as far down as negative 1 for your y min and at least as high as 16 for your y max to be able to see both of those minimum and maximum values. Okay, so that's it. So the highest value is 16, and the lowest value is negative 1. All right. Now, in this picture that you're looking at, notice that the critical number x equals 0 is not a relative min nor a relative max. It's one of those saddle points. So this tells you that the converse of theorem 3.2 is not true. The converse of that theorem would say that, remember converses, we switch the hypothesis and conclusion. The converse of that would be if C is a critical number of f, then f has a relative max or min at x equals c, which is not true. Although 0 is a critical number, it's in the list of 0 and 1 are critical. 0 is a critical number, but it's not giving us a max or a min. So that converse statement is not true. So in other words, the critical numbers of a function need not produce relative extrema. They might not. Okay, that ends this section. I will see you in class.